So I'm going to continue from last time. So let me start by briefly reminding you what I discussed last time, and then we'll continue from there. So last time we talked about communication protocols. We saw some basic examples of interesting communication protocols. And remember, a communication protocol is an object that looks like this. It's sort of a binary tree where every vertex is labeled by a function that either maps the first player's input to a bit, or a function that maps the second player's input to a bit. And then the way you execute this protocol is you start at the root, and the players use their inputs to compute these functions and decide which leaf to go to. Okay, so that's the protocol. And we talked about how this protocol corresponds to partitioning the space of inputs into monochromatic rectangles. Okay, so if you look at what this protocol is doing, then it's basically cutting up this picture into rectangles until you end up with a partition into monochromatic rectangles. So one thing I want to clarify here is that although I draw a rectangle like this, this shaded region this is a rectangle also. This is one rectangle. Okay, so what in general what's happening is when the space is partitioned, a rectangle is just a set R that you can write as A cross B. This is what it means to be a rectangle. Right? It's not really a rectangle in a geometric sense. Okay, it's just any Cartesian product. So this, for example, is the rectangle that's the Cartesian product of this set and this set. Okay, so that's important to note for some of the results that we're talking about. Okay, so we argued that if the protocol has communication C, then you can always partition it into 2 to the C rectangles. And another really interesting fact that I want to prove today is that you can always assume that the protocol is balanced. Okay, what I mean by that is when you look at the description of the protocol, what we're interested in is the communication, right, which is the depth of this tree. But there's another way to count the size of the tree, which is you could count how many vertices there are in the tree, right? And generally, if the tree has depth C, there can be at most 2 to the C vertices. But it's possible that you have a tree that has like order C vertices, but depth C, right? A really unbalanced tree. And it turns out that if you have a really unbalanced tree, that tree can always be simulated, can always be rebalanced. Okay, so that's a lemma I want to prove now, or explain the proof now. So it says that if a protocol has L leaves, or L nodes, in a tree, the number of leaves is essentially the number of nodes up to a factor of 2. So if a protocol has L leaves, then it can be simulated using order log L communication. So in other words, if the tree is really unbalanced, then that's because it's not the most efficient protocol. There's a way to rebalance it so that you actually have log L bits of communication. And why is this true? The basic idea is that, so I'll show you the proof by picture. So suppose someone gave me some protocol that's like this. And it has L leaves total. The first thing I want to claim is that there exists some vertex v in this tree, in this picture, that has roughly half of the leaves under it. Okay. So that such that the number of with L prime leaves under V, and L prime is at most 2/3 of L, and at least 1/3 of L. Okay, so that's a claim. So for example, if the picture looks like this, it's like a long, really unbalanced tree. Then somewhere in here, about halfway down, there's this vertex that has roughly half of the leaves under it and half of the leaves outside of it. Okay. And this is a really simple claim. The reason it's true is, just start at the root, and if the root satisfies this property, we're done. Okay. If it doesn't satisfy the property, go down to the child that has more leaves. Okay. So when you go down to the child that has more leaves, you can only reduce the number of leaves under it, but they can be reduced at most by a factor of 2, because you're picking the child that has more leaves. So initially, say maybe all the leaves were under this vertex, or almost all, then this can go down by at most factor of 2, but it may not go down at all. Like in this case, it doesn't go down at all. But just keep doing this. So in every step, you'll end up at a vertex where the number of leaves is at least half as many as they were before. So the number of leaves goes down, but never by a factor of more than 2. So at some point, you have to hit this interval. Right? So if the number of leaves before this was bigger than 2L/3, then after you go down to a child, you'll lie in this interval. You cannot skip this interval. Okay? Is that clear? Okay, so it's just a greedy algorithm. Actually, this argument shows up in many places in complexity theory. Okay, so there's this leaf which roughly has there's this vertex which has half of the leaves under it. And now we can use this vertex to make a lot of progress in the protocol. So what Alice and Bob will do, they'll look at the protocol tree, they'll find this vertex, they both know the vertex, and they will just say, so their first message will be just announcing whether their input is consistent with this vertex. So their inputs are x and y, and they announce if these are consistent with V. Meaning, if they had run this protocol, would they have reached this V? And that's something they can check together. So Alice will just check on all the entire path here from the root to this vertex. Every time it was her turn to speak, would she have sent the message that they would have led to here? And Bob would also announce whether he would have sent the message that would lead to that there. Okay. And if in fact this V is consistent with both their inputs, they just jump directly to this point in the protocol. So they just send 2 bits here, just saying, am I consistent or am I not? If they're both consistent, they jump directly to here. They reduce the number of leaves they're working with by a constant factor after sending 2 bits. Okay? And the same if they're not consistent. So if one of them is not consistent, they know that in this protocol they will never reach this vertex. So they just throw away this part of the protocol tree. Okay. So basically, after 2 bits, at least L/3 leaves are eliminated. Okay, and that's basically the proof. So they just keep repeating this. So in every step, they'll send 2 bits and get rid of a constant fraction of the remaining leaves. After log L steps, or order log L steps, they'll have eliminated all the leaves. Okay. Any questions? Yeah, so I'll remain at this level of sketchiness, but do interrupt me if you want me to give more details. Okay, so this means that basically if you count the number of leaves in the protocol, the number of vertices, it's the same as counting the depth. It's either log the number of vertices or the depth. It's essentially the same in terms of the complexity of the protocol. And that's very useful because, as we'll see today, sometimes it's easier to design an unbalanced protocol tree from a design perspective. It's a more natural protocol than coming up with the balanced tree. Okay, and we'll do that later today. So what I want to do next is I want to sort of use our first tool for analysis of the complexity of communication protocols. So we've talked about communication protocols, and we've talked about the basic idea. We want to find the most efficient protocol. The first quantity that's going to be very useful for understanding the complexity of these protocols is something that we've all seen before. It's the rank of this matrix. Okay? And that turns out to be a very natural quantity and makes a lot of sense here. So the rank. Okay, so say we have a Boolean matrix and we want to compute it using a communication protocol. Then we could look at its rank, and let me just remind you what the rank is. So throughout I'll be thinking about the rank as a quantity over the real, as the rank over the reals. Okay, and what is the rank? It's so the rank is R. Okay, and this is a definition, but there are a bunch of equivalent ways to describe the rank being R. So rank of the matrix M. So one way to think about it is R is the smallest number such that M has R linearly independent rows. Okay, and you can also write here columns. It doesn't matter whether you look at rows or columns. Okay, so it's the smallest number of, largest. Largest. And R is the smallest number such that M can be expressed as A times B, where say M is an M by N matrix. Okay, so it has M by N. Then it's the smallest number, so you can write M as A times B, where A is an M by R matrix, and B is a R by N matrix. Okay. And another way to define it is R is the smallest number such that M is the sum of R rank 1 matrices. Okay. So these are sort of standard facts that I won't prove, but I hope you believe them. But given the definition, and especially this third bullet, you immediately, and our characterization of protocols as partitioning the space into monochromatic rectangles, you immediately get some relationship between the rank and the communication complexity. Okay, and that is So this claim that if M can be computed with C bits, then the rank of M, I claim, must be at most, any guesses? 2 to the C, right? And that's because M can be computed with C bits. That means you can partition the matrix into 2 to the C monochromatic rectangles. And each one of those rectangles is a rank 1 matrix, right? So I can look at the matrix, take one of the rectangles, this one, and I can write M as a sum of all the 1 rectangles. Okay, so if there are 3 1 rectangles in the matrix, then M is equal to this sum, and each one of these matrices is a rank 1 matrix. Okay, so by the third bullet, this means that M must have rank at most the number of rectangles here.
For every field?
For every field, yes. Yeah. So usually when I say rank, I'll be talking about only the rank of the reals. And if you want to work with, say, another natural field to work with is GF2, but the rank over GF2 is always smaller than the rank of the reals. Okay, so this is a stronger statement than the rank is small. Okay, and another inequality is that so another lemma is that the communication complexity is always at most the rank. Okay, and that's another fact that's somewhat easy to see, but let me explain why that's true. It follows from this fact that I just said, that the rank over GF2 is always smaller than the rank. So if the rank is this, that means the rank over GF2 is at most that. And that means that so if you look at the matrix, that means the number of, so again, sketch the proof. So the number of distinct, the first claim is that the number of distinct rows is at most 2 to the r. And the same thing applies to the number of columns. Okay, and that's because if the rank is only if the rank is only this quantity, that means the rank over GF2 is also only that quantity. And if you have only that many linearly independent vectors over GF2, you can generate at most 2 to the rank m distinct rows as linear combinations of those vectors. Okay, so there are only 2 to the this many distinct rows and at most that many distinct columns. So if you're a player, you just need to say which one of those rows your inputs correspond to, if you're Alice. And Bob just needs to announce which one of those columns his input corresponds to. And that's a communication protocol that solves the problem. Okay?
Is it somehow obvious that the GF2 rank is smaller?
It's a little bit ugly. You can first, the way to prove it is you first think about the real rank. For a Boolean matrix, the real rank is the same as the rational rank. That's one thing you can check. Okay, like it doesn't help to use irrational numbers. And then you can say the rational rank is only bigger than the GF2 rank because, then you can move to integers. Once you have rational linear combinations, you can move to integer linear combinations. And then basically being linearly independent over integers is only stronger than being is only weaker than being linearly independent over GF2. Okay, so you can check. Okay.
From writing the determinant, so you can write the determinant and then you have the modulo operator. Okay, so that's only for prime fields. Sorry. Okay. Yeah, for prime field it's easy, but never.
Yeah. There's a step that has to do with getting rid of the non-rational numbers. It's a little ugly. Yeah. Okay, but I don't want to do it. It's not particularly insightful. Okay, but that means that basically once you know the rank is R, essentially the problem gets reduced to a matrix of size 2 to the R by 2 to the R. Okay, there are duplicate inputs that have the same behavior if the matrix is bigger than that. So given these two bounds, it's very natural to ask, what is the right relationship between communication complexity and the rank? Okay, and that is the main thing that I want to focus on today. The first observation, you can ask, which side here is tight, right? Is it always true that the communication is close to? This says the communication is at least log of the rank. Okay, and this says the communication. So putting these two together, it says the communication is at most the rank of M, and it's at least the log of the rank. And the first interesting fact is that this bound is not tight. So there actually is an example of a matrix where the communication is at least log to the power, 1.3 of the rank. Okay, and it's a strange example. I won't do it, but there is an example. So we know that it cannot be perfectly tight. But there's no better example. Okay, so a famous conjecture of Lovász and Sachs, which is still open, is that the communication is always actually bounded by a polylog of the rank. So this is to Lovász and Sachs. Okay, and today I intend to give you a sketch of the best known bound for this problem, which was only proved last year or 2 years ago, which is a theorem due to Lovett, which says that the communication is at most square root of the rank times some polylog factor, times log of the rank.
So you're not going to do Lovett's proof, are you?
I'm going to sketch it.
Compared to like Rothfuss's thing? Or?
Oh, I'm going to sketch Rothfuss's proof. Yeah. Okay. So that's the main thing that I'm going to try and do today. But actually, before I do that, let me show some other results. So these are upper bounds using the rank. But this direction is also really useful. This direction allows you to prove lower bounds using the rank. And many of the problems that we're interested in have really easy lower bounds using this inequality. So let me spend a few minutes telling you about those, and then I'll try to spend most of the time proving this theorem. Yeah? No, I think it's just stated like this. Yeah, just because we cannot find anything better. The counterexamples here, I think for a while there were a sequence of works that got sort of slightly better counterexamples showing that this is not tight. But at some point then people started writing papers like no such counterexample can give better, and that's when that line of research ended in the 90s. Until Lovett really renewed interest in this by proving this bound. Okay, but for a second let's go back to thinking about the other direction. and see how this characterization already, I want to show you that it actually already helps you to understand many interesting functions, many interesting problems, the rank of them. So let's do a few examples. The first example is equality. Okay, it's kind of trivial. So in the equality problem, you know, Alice is given X, Bob is given Y, and they want to know, you know, is X equal to Y? So I told you last time that the only thing you can do is a trivial protocol, send, you know, Alice has to send X to Bob in the deterministic world. And now, given this characterization, it's very easy to see that's true, because what is the matrix of this function? What is the matrix of this function? The identity, yeah. So clearly has full rank. And so by this lower bound, this means that the number of rectangles you need is, you know, the full, okay? So it means that if you're working with the n-bit strings here, this is a 2 to the n by 2 to the n matrix, and it has full rank. So its rank is 2 to the n, so C must be at least n. So this says, so the rank is 2 to the n, so C must be at least n. Okay. The next, so another function that's interesting is the greater than function. Alice and Bob have two numbers, x, y, and they want to know is x greater than y. Okay, and again, you see that the matrix now is something we all know. It's basically an upper diagonal matrix or lower diagonal, I don't know. And again, it has full rank. Okay, all the rows are linearly independent, so C is at least n. If now I'm thinking of x and y as n bit numbers. Okay, so for this calculation it makes sense. A slightly more interesting example is a function we talked about last time, the disjointness function. So here, Alice and Bob, Alice is given a subset X of 1 through n, Bob is given a subset Y of 1 through n. So let me write dn. So let me write dn for the matrix of this problem. And this one is a little tricky, but okay. So let's look at what is d1. So d1 is so in the universes of size 1, you know, either X has the lone element or it doesn't. So this is a 2 by 2 matrix, and it's this matrix. So if it's in both, it's not disjoint, and otherwise it's disjoint. Right? It's only if the element is in both the sets is it intersecting, otherwise it's disjoint. So that's the matrix, and you see that it's full rank. Okay? And what is dn? You can write it like this. It's actually so let's split it like this. Let's write here all the rows that correspond to sets where 1 is in the set. Okay? So these are all the x's such that 1 is in x, and here are all the x's that 1 is, or let's go with n. N is in x, and here n is not in x. And similarly, I'll write here all the y's where n is in y, and here n is not in y. And then you see that here you just have a 0 matrix, because n is in both, so they're intersecting. And what matrix do I have here? Sorry? dn minus 1, exactly. dn minus 1, because the nth element doesn't matter, and it's just disjointness on the rest. And in fact, that's what you have everywhere else. So everywhere else, the nth element does not matter. Okay, so the rank of dn, you see, is exactly twice the rank of dn minus 1. Okay, so that proves that, again, the rank of dn is equal to 2 times the rank of dn minus 1, which means that it's equal to 2 to the n. The rank doubles every time you add one element to the inverse. Okay, so again, this means that the communication must be at least n. And the same proof applies to yesterday. We talked about k disjointness. This one is a little more complicated, so I won't do the proof. But I'll just tell you that so here Alice gets x, Bob gets y, and the size of x is equal to k. The size of y is equal to k. What you can show is that this matrix also has full rank. The proof is not as simple as that, but the rank is actually, it's exactly what you expect. So it's, the rank is exactly n choose k. And that means the trivial protocol is essentially the only protocol. Okay, or that's the best protocol. Okay? Yeah? What is a similarity transform?
Like Gaussian elimination of rows or columns.
Mm-hmm.
So, but that clearly isn't true because you claim that the common example showing, it's bigger than log to the 1.3 times or something like that.
Does that mean that it's not preserved?
So, because otherwise you could just do Gaussian elimination.
I see.
Yeah.
To make it a full matrix. Yeah, you're right.
So that can't be right. But are there other invariants, like maybe certain subclasses of the transform?
That's a good question. I haven't. There's no. Yeah, there's nothing interesting really that I know how to say in that line. Yeah. I can't think of anything else to say that satisfies that. Okay, so the rank immediately gives us a way to argue lower bounds for deterministic protocols in many cases. So you see, well, once you see this, you can kind of get a feel for why Lovász and Sachs started to feel this must be really, it's capturing the communication in so many examples. So maybe it's really is the communication. Okay, so now what I want to do is, in the remaining time, focus on trying to prove this theorem, which is the best upper bound we have on the communication in terms of the rank. So let me do that. And actually, this is the proof here. What I'm going to show you is a simpler proof than what Lovett discovered, but it's still kind of a nasty proof, at least I think, in the sense that, like the protocol that I'm going to get, I'm going to describe to you a protocol, but then the final protocol, the one that proves this bound, is really, I don't know what it's doing. Okay, it's not a natural protocol. The overall proof will have a lot of geometric intuition, but the final protocol will go through that rebalancing step that we did. And then kind of all the intuition will just get messed up. And I actually spent quite a bit of time trying to, a week, trying to guess a proof that is really nice and geometric. You'll see that there's going to be a lot of geometry in the proof. So it seems to me that there should be a protocol which is nice and geometric. But I don't know one. So that would be, to me, very interesting. If you could prove even this bound, but using a very natural protocol. Okay. So let's see how to prove this bound. The main idea, so there's going to be a main technical lemma. And first, let's start by showing how that lemma can be used to prove the bound. So let me dig up the exact statement so I won't mess it up. Okay, so here's the main technical lemma. Okay, and we're going to prove this lemma by appealing to some fact from convex geometry, which I'll explain. But it says that so it says that any Boolean matrix, so any 0, 1 matrix that has of rank r greater than 1 has a monochromatic rectangle of density at least 2 to the minus, okay, the constant's not important, but it has a rectangle of density 2 to the minus essentially square root r. Okay. So we were trying to prove that any rank r matrix has communication square root r. Now, if it has communication square root r, then definitely there's going to be, that means you can partition the whole matrix into 2 to the square root r rectangles. So certainly one of those rectangles, the average rectangle, will have density 2 to the minus square root r, right? Because there will be 2 to the square root r rectangles total in the end. So the first step is just to prove this weaker conclusion. Instead of finding a protocol, we'll just find one large rectangle. Okay? That's what this main lemma will do. And now I want to show you how this already gives you a protocol. So if you can always find a large rectangle, a rectangle of density 2 to the minus square root r, then actually you can use that to get a protocol with communication square root r. Okay, so that's the first thing I want to show you. Okay, so is a high level clear of what I'm doing? Yeah. Yeah, the number of the number of entries. So if it's like a m by n matrix, that means this rectangle will have m n times this number of entries in it. Okay, so it'll cover that fraction of the matrix.
For example, for full rank, it's somehow obvious or not?
Even for full rank, it's not obvious to me. I don't know. Does anyone see any statement for full rank? Two to the minus r. Yeah, that's a good question. I don't see a simple proof even.
But what do you mean? So I mean, just choose m or n. One is min, right?
Choose okay.
Choose that row. Choose whichever columns have zeros or ones, whichever is a larger fraction. You pay a factor of 2.
Oh, you just choose one row. I see. Okay. Good. Yeah. Yeah. So if it's full rank, then we're basically looking for. So there only are rows and columns, and it's enough to find one column or one row. Right? That would be one over r fraction. And Zankur says, so let's pick an arbitrary row and take either the zeros or the ones of that row. Okay, good. Great question. Okay. Any other comments or questions? All right. So let's assume this statement, and then let's see how to continue. So now I want to use a statement. The first thing I'm going to do is I'm going to use a statement to define a protocol which may not have small communication, but it's going to be a protocol tree that has a small number of leaves. Okay, the leaves will be like roughly 2 to the squared r number of leaves. And here's that protocol. Here's the intuition. So suppose so you have the matrix M, and you found a rectangle that's large that has this density. So let's say this is that rectangle. Okay. You know, I can rearrange the columns and rows to put the rectangle in this position. And now let's call these parts okay. So here's a simple claim. It says that the rank of AB or RB plus the rank of RA must be at most the rank of M plus 3. Okay. And that's really easy to say. It follows from so if you so let's see. So you can write the rank of RB plus the rank of RA that's at most the rank of A plus the rank of B plus 2. Okay, because the rank of this matrix is off from the rank of B by at most 1. Because the rank of R is, so you can write this matrix as 0B plus R0. And R0 has rank 1. Okay, so that means this matrix has rank that's within 1 of the rank of just B. And the same is true of this matrix. Okay, and so this thing is equal to exactly the rank of 0 A, B, C plus 2, right? The rank of this matrix is the same as the rank of A plus the rank of B. And now I'm going to do the same trick. So again, now insert the R back in. So it's at most the rank of R, A, B, C plus 3. Okay. So the basic operation I'm doing is that if you have a matrix and you're adding a rank 1 matrix, that can only change the rank by 1. And that's again by the third bullet in the definition of rank. Okay, so adding or subtracting. Okay, so kind of by manipulating these matrices, you can eventually construct R, A, B, C. And this means, okay, this is really good because it means one of these two matrices has half the rank. Okay, so suppose RB has half the rank. Then what should happen? Well, if you're Bob, you know whether your input is consistent with R or not.
But I'm confused about something. So you're saying rank of A plus rank of B equals rank of 0, A, B, C? So what if A and B are 0 and C is the identity?
It's an inequality. It's an inequality, right?
Okay.
Yeah.
What you say that if we go to the, we assume going to the negations and losing 1 in the rank maybe, that R is 0. If R is, tangle is 0, it's okay.
If R is 0, it's very easy, but actually I need it for both. I don't think you can just go to negations.
But just if we switch to the negation, the rank changes by 1.
Oh, I see, by adding 1. Okay, yeah. Yeah. It's roughly the same. Yeah, but yeah, I actually only need the inequality. So I mean, if there are, k independent rows here and k prime independent rows here, then there's certainly k plus k prime independent rows here. So it's okay, good. Okay, so just ignore the 3 for now. This means that roughly one of these two has at most half of the rank. Okay, so suppose RB is the one that has half of the rank. Then what should happen? Bob should announce whether his input is consistent with this side or this side. Okay, so if Bob says my input is on this side, the players have made a lot of progress because they're now in a matrix which has half the rank. Okay, they can do that at most log r times. Okay, they can keep going to that side at most log r times. On the other hand, if Bob says my input is consistent with this side, that's where we use the fact that this matrix is relatively large. R is relatively large. That means that the number of entries in this matrix got reduced by 1 minus 2 to the square root r fraction. Okay? So that's the idea for the protocol. So in every step, they both, they have some canonical way of picking out this largest monochromatic rectangle. And then one of the players, the one who can sort of has this option to reduce the rank by 2, will announce whether his input is consistent with that option or not. Okay, and they continue in this way. And so now if you look at the protocol tree, so whenever they go left, this direction, that means the rank gets reduced by the rank over 2 to rank over 2. And this direction, the size of the matrix gets reduced by size times 1 minus 2 to the minus square root r log r. Okay, by this factor.
Say it again, what is the density? Do you assume that R is quadratic matrix or not?
No, it's not.
No, that's my...
So it's the number of entries. So I'm counting just the number of entries. So if this is a m by n matrix, R has at least m n times 2 to the minus 20r.
And then it doesn't mean that the size is reduced.
No, it does. Because certainly the area of this is less than the area of, the area of this is 2 to the minus square root r fraction. So this area is at least, yeah, I'm measuring the area. Okay. Actually, a stronger thing is true, right? The area of A, B, and C is bounded by this number. R has 2, so actually all 3 together. Okay. Okay, so what you get is a really unbalanced tree. You can only go to the left log r times, and you can go to the right roughly 2 to the square root r times. Okay, so if you count the number of leaves in this protocol tree, it's like the same as counting the number of binary strings which have at most number of binary strings of length 2 to the square root r that have at most log r ones. Okay, so the number of such things is, the number of leaves here is basically 2 to the square root r log r to the power log r. Okay, so I'm going way slower than I want to. So that's the idea. So you count the total number of leaves, and then you apply that lemma that's written above. So then you get a protocol which actually has communication that's like square root r log r. Because we start with a tree which has number of leaves that's bounded by 2 to the square root r log r.
Is this main lemma known to be tight, or is it
that's a very good question that I should know the answer to, and I think it's tight, but I remember someone saying that it's tight, but I don't know the proof. Or maybe do you know if it's tight?
Well, it may be tight, but I think if it's tight for like silly reasons, in the sense that the actual matrix for which it's tight is only like r squared by r squared or something, which would have like a trivial communication protocol. Or
if it's r squared by r squared,
there's some like the geometric thing. I mean, they use John's theorem, right?
Right.
That part's definitely tight.
No, if it's r squared by r squared, it can only, a single entry is density 1 over.
So it's not this part that's tight, but
Okay.
there's something else. But if the thing that produces it doesn't nearly have enough rows or columns to be interesting, is what I seem to remember.
Okay. Okay, so that's
So is there an n that shows up here?
n. No.
So
The n the n actually in the whole problem disappears because you might as well assume that the matrix is 2 to the r by 2 to the r.
right. So but if you do this to the root r times, you're only decreasing the size by a constant factor.
Yeah, that's a good point. So that's exactly what I just said. So you can, without loss of generality, assume ahead of time that the matrix is 2 to the r by 2 to the r. So then you do this 2 to the squared r times, and then you need to do it r more times.
Okay.
Like you actually do it r times 2 to the squared r times. Okay, and that r factor outside doesn't matter. That's an additive plus log r. Okay. Yeah. So the way you prove termination of this protocol, you say eventually the matrix disappears. If you go like r times 2 to the squared r times to the right, you're down to a submatrix of size 1. All right, so now let's see. I wanted to have half an hour to do the next part, but I guess I have 10 minutes.
So by the way,
So try to.
this part though can't be tight. I mean, it can't be known to be tight.
Because.
Otherwise, log rank would be false.
Oh, you're right. Yeah, right. Good point. Yeah, if you had a counterexample here, right? So if the log rank conjecture is true, then we do know that there has to be a rectangle of density 2 to the minus polylog r. So yeah, so one way to disprove it is to show that this is tight. Good, yeah. More questions or comments? Okay, so we wanted to understand this thing about rank and communication, and now we completely got rid of the communication. We just want to in some sense, understand this pretty combinatorial lemma. And I'm going to give you some intuition for why it's true. And I'm going to run out of time. But I'll try to give you some intuition. So the main technical theorem from geometry that's useful here, so I'm going to try and prove the main lemma. So let me tell you a really nice theorem. So the Theorem Convect talks about convex bodies in Euclidean space. Okay, so it says that if K is a convex body in r-dimensional space, and it's symmetric, so symmetric means if x is in K, then so is minus x. Okay, so it's symmetric around the origin. And the unit ball B1 is the largest ellipsoid that's contained inside K. Then K is contained in B squared R. Okay, so this is the ball of radius squared R. Okay, so what it's saying, so you have some convex body. And in general, convex bodies can be very long, right? They could have points that are very far away. But what this says is if you sort of have a convex body that is reasonably nice in the sense that the largest ellipsoid you can draw inside of it is a unit ball. Okay, so that means it must be somewhat balanced. It can't be like very long and skinny. Otherwise, there would be a larger ellipsoid that would also be long and skinny.
In terms of
volume. Okay. Yeah, in terms of volume. So if this is the case, if the unit ball is the largest ellipsoid, then if you look at the ball of radius square root r, that contains the convex body. Okay, which means that in particular every point in K has length at most square root r. Okay, so let's see how to use this fact. So now I'm going to use this fact to make a claim about Boolean matrices. So the claim is if the rank of M is equal to R, then there exists vectors V1 through, so say this is M by N, V1 through Vm, W1 through Wn, that are R-dimensional. Okay. So what I have so far is just the definition of rank. Okay. So if the rank is R, then I know that you can find a vector for every row, a vector for every column, such that in R-dimensional space, such that the corresponding inner product is equal to the entry. Okay, that's the. Okay, so I didn't write it in that form, but that's the second bullet in the definition of rank. Okay, but what I'm going to prove using John's theorem and the fact that M is Boolean, or what's true, but I will not prove, is that you can have the additional property that all the VIs are of unit length, and all the WJs are of length at most square root r. Okay, so what's the idea of the proof? Well, consider the convex body K. So let's start. So let's start with V1 through Vm and W1 through Wn that don't satisfy the length condition, that are not short. Okay. I'm trying to represent this matrix by vectors which are actually short. So we know we can represent this matrix by some vectors. So let's start with some arbitrary vectors. And then you set K to be the convex hull of W1 through Wn and minus W1 through minus Wn. So K is a symmetric convex body. Okay, so it's kind of almost fits John's theorem, but not quite. And then the idea is, if this body doesn't necessarily fit John's theorem, the largest ellipsoid that's contained in it may not be the unit ball. But what you can always do is apply a linear transformation both to the W's and the V's. So like, imagine scaling in a particular direction by multiplying for the W's by alpha and by dividing for V's by alpha. This will preserve all the inner products, but it will change the largest ellipsoid. Okay, like, so if in one direction this convex hull is really long, you'll shrink in that direction and increase in the other direction. And it turns out that you can always do the scaling so that you have these properties, and K actually has the unit ball as the largest ellipsoid that's contained in it. Okay?
When you scale W, you still have the V's on unit sphere or what?
No, we don't know anything about the V's. Okay? so far? So far, we just know these are W's. We'll scale the W's so that this K has its largest ellipsoid is unit ball. And then we look at the V's after that. So we do that to the K's. We also have to do that to the V's to preserve that V's and W's represent M. So that's where we are so far. And now, because K fits the hypothesis of John's theorem, that means K is contained in the ball of radius squared r. So all of these W's are also of length at most squared r. Okay? So we're almost there. The only thing we need to now check is what are the length of V's. And to do this, what's the length of V? So let's write EI to be VI divided by the length of VI. And then I can write the length of VI is equal to the inner product of VI with EI. Okay? So EI is just a unit vector in the direction of VI. And the length of V is just the inner product of VI with EI. Now, EI is in the unit ball, okay? Which, by our construction, is contained in the convex hull K. Which means you can write EI as a linear combination of these guys. As a convex combination of these guys, actually. Okay, so actually this inner product you can write as some convex combination, mu j, vi, wj, and maybe there will be other terms, minus, there'll be minus terms also, gamma j. I guess you'll never have the minus term. Okay, never mind. I'll just write it. Okay. The point is you can express EI as a convex combination of these things because EI is contained in K. And now we're almost done because VI inner product WJ by construction has magnitude at most 1 because it's an entry of the matrix and the matrix is Boolean. Okay. So all of these numbers are at most 1 and we're taking the convex combination of 1. So this thing is at most 1. Yeah. Okay. So that's a very quick proof of this part. So now I will attempt in a couple of minutes to give you an intuition of how the rest of the proof goes. I won't do it. So now we ended up with this claim, which says that you can represent this matrix using vectors where all the VI's are unit vectors and all the W's are squared R length vectors. And that means that for any pair of VI WJ, you have that. So if I look at so let's say VI is here and WJ is here. There are two cases. The first case is Mij is 0. In this case, the two vectors have to be orthogonal, right? So this angle is exactly 90 degrees. And the second case, if I just look at the direction, so I just care about the angles now, okay? In the second case, the inner product has to be 1. So the picture should look something like this. But because WJ has length at most squared R, actually you can argue that this angle here is at least omega 1 over squared R in this case. So what you can show is that because this is a short vector which has inner product 1, this angle here must be 1 over squared R. At least 1 over squared R. So it's large. So there's a big difference between these two cases. Here the angle is exactly 90 degrees. And here the angle is at least 90 minus 1 over squared R. And this means what you try and do is you define this rectangle. So you pick z1 through, for some parameter t, t I think will be roughly 2 to the squared r. You pick z1 through zt random unit vectors. Okay, so random vectors of length 1. And you define the rectangle R to be all ij such that vi has positive inner product with z, zk is bigger than 0, and wj zk is smaller than 0 for all k. Okay? So you sample completely random unit vectors, pick all the vi's which have positive inner product with all of them, and all the wj's that have negative inner product with all of them. And what ends up happening is, so this is a rectangle, right? Because this is a subset of the vi's, and it's a Cartesian product of a subset of the i's and the subset of the j's. And moreover, this rectangle is more likely to have these pairs. Because for these pairs, you include such a pair only when the z's are here. Okay? This is a vector that has positive inner product with vi and negative inner product with w. And here, if you look at the corresponding area, it's slightly smaller. It's this region. Okay, and this angle is at least 1 over square root r. So, okay, so it's fast. But if you take many samples, what ends up happening is you're much more likely to be include entries in the rectangle that correspond to inner product 0 than to include entries which correspond to inner product 1. So that's the basic intuition. So you can show that in expectation, using this probabilistic argument, you can show that there is a rectangle which has way more zeros than ones, and then you can actually make this, you can get rid of the small number of noise that you have to find a truly monochromatic rectangle. Okay, so sorry I went overboard. I'll stop there. But thank you. Yeah. So the expected size you will get here is like 1 over 4 to the power t. Okay, so the size comes from, it'll be like 2 to the minus square root r. Okay, and it'll also be very unbalanced. So it'll have way more zeros than ones. And that's the key step that allows you to find the monochromatic rectangle. Okay. Thanks.